cars could be created. Could be created to identify defects more accurately than a person, resulting from the sensors on board, as well as the frequency at which they collect data points. In 2019, approximately 421,000 workers were reported to have suffered from non-fatal injuries in manufacturing workplaces, according to the United States Bureau of Labor Statistics. Our goal is to further develop that the further development of this gantry system could lead to the reduction in these statistics.
So as for the proposed solution of our project, so we'll be constructing a sorting system on a new gantry, since this is a project that we inherited from the previous Univ Design 2 team from the previous semester. So so the deliverables would be to change and improve the pre-existing lateral logic code to make it compatible with the new gantry, but also to reconfigure the motors that were provided by OMRON. Another thing would be to implement and design an HMI system for controlling error checking, and that would be really helpful for like operators if they use it, for example, in the field, where they'll be able to basically detect how many shapes, or I mean how many colors that the sorting system have sorted, and also for error checking, for example, if the PLC communication is lost, then the HMI system would be able to basically have a pop-up message and tell the operator that something was going wrong within the communication. So those two pictures right here are the old and new gantry that we had. So the one on the left is the old gantry that was powered by the micro step drivers, and then the one on the right is the new gantry that was provided by IGUS with powered by the OMRON motors. Next slide. So as for the engineering specs, they were mainly split into three main sections: motor, vision system, and finally HMI. For the motor specs and motion, so the maximum target velocity, which is the velocity at which the motors can move before we can get any response or instability. So the X and Y axis would move like 8 inches per second, and then for the Z axis, 2 inches per second. And then as for the ideal target velocity, which is the velocity at which the motors can operate at their peak velocity, making the gantry system work at its best for performance. So for the X and Y axis, it's going to be 7 inches per second, and then for the Z axis, it would be 1.5 inches per second. As for the scaling, which is how we configured the motors in the Sysmax Studio software. So all motors use 5 million pulses per revolution, which gives the X and Y axis a range of even the Z axis 1.189 inches per revolution. Next slide. So this picture right here shows how we configured the X, Y, and how we scaled the X, Y, and Z axis. So we had 5 million pulses per revolution, and that would correspond to 1.189 inches per revolution. Next slide. So as for the vision system can extract a range of up to 8 colors, which is more than sufficient for our project, since our project detects 4 colors. And then for the focus and brightness, it must be determined manually. As for the HMI, the operating temperature of the HMI ranges from 0 to 50 degrees Celsius. And so it's mainly used indoor. The resolution is 1280 by 800, which is sufficient since we're using it indoor. And then the memory is 900 megabytes. Next slide.
Okay, as for the overview diagram, we've basically split up our project into 3 main parts: the PLC section, the gantry, and the vision system, and then we have some future deliverables. So basically, to get started on like what we had did this semester is first we had to take the old gantry system that was used last semester and make sure that it worked properly before we could continue on to our new system. And that actually gave us a little bit of problems that we'll talk about in the setbacks. But after that, we had to research on how we wanted to construct the new gantry from IGUS from a mechanical standpoint. And then from there, or really at the same time, we were doing that, and then also working on creating or improving the PLC code for the new OMRON motors, and then adjusting the vision system parameters so that it has better object detection. Some of the accomplishments we had, like I said earlier, the first thing we did was basically run the old gantry system and make sure it works. So I have a quick video I'm going to show in double speed. So you see there's a red triangle that goes along. It picks up the object and places it in its desired location. And now we'll put a green triangle, and because it is a different color, it should be placed in a different location after the vision system detects it. And you see that that works properly. And so for all shapes and colors, we have a different designated spot that we coded into the PLC program. Okay.
So for a couple of the other accomplishments, so we, of course, moving to a new gantry, we were using new drivers and new motors. So we configured the PLC code to work for the new hardware, and that gave us a couple of a couple issues, but we got past that. And so that's one major thing that we had to do. We had to basically change all the settings. And as Rauf was saying, the configurations and the numbers for the new motors were all different than they were for the old motors and drivers. And so that was part of it. Another big thing that we ran into that we managed to get done was we adjusted the vision system parameters to accurately identify the objects. So like as you can see in the bottom left, this is a picture of the vision system interface, and it's correctly identifying that that's a red triangle. I mean, sorry, a green triangle. And that's and in the beginning when we started, we'll talk about it in the setbacks, but in the beginning when we started, it would either not recognize things at all, or it would recognize the wrong color, wrong shape, due to like brightness issues or the parameters that were already set in place. So we had to make those changes, and that's something that we got done successfully. And so we ran into a few setbacks. So what the most major issue that we had was that the IGUS gantry, the gantry was provided to us by IGUS, and the motors are provided by OMRON. And so the two parts were essentially incompatible. So we were never actually able to attach the motors to the new gantry system. So we weren't able to test the motor settings on the gantry. So to try and get around that, to try and solve that problem, really, we took some measurements and we ordered the couplers and adapters that we would need to attach, the motor shafts to the gantry system. And we got those parts, I believe, like in the last few weeks of the semester. And because they came in so late, we weren't able to attach everything together. So that was one thing that we never got to do. We have lots of like settings in place, but we weren't able to test them on the gantry system itself. A couple of communication errors that came up between the driver and the PLC. There's the one at the bottom of the screen that you can see there, the error stop input. So we had to get with the sponsor and work with their technical support to basically troubleshoot that problem. There was a bit that was staying active that should have been inactive, and it wasn't allowing the Y-axis motor to run properly. And so now that one is working properly. We had some wiring issues with the hardware. The conveyor belts had some issues, and it wasn't communicating with the PLC properly. And we managed to, after a couple hours of troubleshooting that, we managed to get that done. And as I said before, the vision system in the beginning wasn't working well. So we had to change the parameters. We had to put in the RGB values that we wanted the camera essentially to look for, and get through that.
Now I'm gonna go over like a quick demo video of kind of like what we were able to get done with this semester. So essentially all we wanted to do is we knew we had everything from a software standpoint completed. So we wanted to make sure that we could mimic what the old gantry system was capable of doing with our new motors. And so let me go ahead and play this video. So obviously this is our gantry system we're waiting on parts for. You can see that everything's turned off. I'm going to press start on the HMI. And the motors are going to establish a homing position, which is what this is. And once they've stopped, they're ready to pick up an object. And now you should be able to see the conveyor belt is moving. So we will go ahead and place an object on the conveyor belt. You'll see that it'll detect it correctly. And then the motors will begin to turn again to basically mimic like going to pick up the object and place it in its desired location. So you see that they're moving here now, going to pick it up, and then they should spin back to go back home and stop. And then we can just show that like one more time, that we can put a different shape and color on there, and the motors will move in a different direction essentially, because this is a different object. You can see this is the Z motor. It's going to pick up and pick up the object. Then the X and Y motors move to go place it, and then it will return back to its stationary position. Kind of let that run through, and that is pretty much it. Hold on, let's go here. Okay.
So in summary, we have made some adjustments to the programming to function with the OMRON motors and the drivers, as well as configure the new motors to communicate properly. All that's left to be completed for this project is to couple the new motors with the IGUS gantry system and secure extrusions to the gantry system to lift it up and provide enough room for the Z-axis motor to maneuver.
All right, that is pretty much it. That is our references, and that will conclude our presentation.
Okay, thank you. I think I see Tommy and Carrie Galloway are both here now. So Alan, would you start asking the question? And before you ask the question, would you say a few words to introduce yourself to the students? Then I think Tommy and Carrie can follow you.
Sure, I'm Alan Goodrum. I'm retired after 40 years in the computing industry, primarily Texas Instruments and Compaq and HP. So we've got lots of experience in building or designing things for things to be manufactured. So it's always in product development. So I can see, or as I've never been in the factory doing the automation things, but I can see where factory automation is important. I did so in the section that you called engineering specifications. What I saw was a list of specs for your parts, if I understood it right, how the motors worked and things like that. So what I was expecting to see is specifications for your design. Did you have constraint that said that you had to be able to pick up pieces this heavy or sort them at this speed? How do you know, just because it works, how do you know that it works the way it's supposed to? What were your input constraints that said, that your boss, somebody came in or your customer came in and said, I need something that does this. Did you have a list of what's the boundaries of what this is? How big, how small, how fast, how slow? Those kinds of specifications for what you were supposed to do, or what the thing was supposed to do when you were finished.
So yeah, I'm not sure if we had mentioned it earlier or not. I don't remember, but essentially the idea was we wanted to sort four colors and 3 shapes. So rectangles, triangles, circles, and then the colors would be blue, green, red, and pink. And so that, like, just doing those 12 unique like iterations was like a pretty big challenge. But those are the main specs that we wanted to get through. As far as weight and things like that, we didn't have anything specific. We had the idea of these shapes with the magnets attached to them so that we could move them. But that was the basic idea. It was being able to identify and sort those 12 unique shapes and colors.
Okay.
Did that answer your question?
Yes, if that's your if that was what you were assigned, and that was the specification of what you were supposed to do. In most applications, you're going to have a lot more constraints than that. So be prepared for that in the real world.
Yeah, the rest of the constraints were all like physical constraints for the motors that we were using and the gantry and the size and all that. We just chose not to show it here. We wanted to just keep it more higher level.
Okay.
Okay, Tommy?
Yes. So I'm Tommy Cooper. I'm a double graduate from University of Houston. I had both the BSEE and an MSEE from U of H. So I have specialized more into medical devices, but it includes all manner of mechanical and electronic hardware that you might imagine. Everything from in our lab right now, we have robot arms and pressure infusers for the Army, and a couple of laser projects measuring things in the body and treating people with that. And we have probably about 10 to 15 projects ongoing right now. So it's kind of a wide range of things, but so that's my background is that where I've been doing it a long time. And right now I'm still doing that. I'm still working. I have a consulting company and actually have both of my sons who are engineers working with me. So in thinking about what you're doing, kind of following some of Alan's clues, I mean, that was fairly impressive to see it did recognize the color, and I couldn't quite tell whether it was recognizing shape, but I think your point was that it did. And so those are things that I think from a viewpoint of a basic, simple set of goals, usually we get much tougher goals than this in terms of more specificity and so forth, like how fast you do it and kind of how long it will last, how long it will run. Now, there was one thing I did notice, and I mean, it's a good operating range to go from 0 to 50 degrees C, but your comment that it therefore would be used inside, that's a pretty good range for an indoor product even. You might want to, the indoor products usually are maybe 10 to 40 degrees C, and even that's a fairly wide range. That 40 degrees C is still 104 degrees F. But the fact that it can run over that range and you have extra range for that is a good thing. So my kind of caution to you there is be careful with your specs. It's something that I deal with all the time in terms of being able to write specifications and paying attention to the customer's need and the use environment. Sounds like your product or your work would be used in a more of a factory setting. And so it's a relatively controlled environment. It's not quite like being in an office. Is that true? Is that part of what you were given, or did that come up?
Answers?
Yeah, so I think the idea, so working with the professors and things like that, I think the idea was this was going to be used in the lab. Because the other projects that also use this gantry system, there are other projects that are going to be using this gantry system and this PLC. So those are going to be in the lab. And one of the goals of the project initially was to show prospective UH students who were touring the lab and things like that, the capabilities of a PLC. So another group, like they did name etching into like cardboard using the PLC and the gantry movement. So they were able to do that, and so it's trying to show the different capabilities of this PLC. So I think in terms of the environment, it wasn't really taken like we did consider that it would be a controlled environment and not necessarily outdoor or in a very hot and like operating environment.
So unfortunately, I missed a little bit of your presentation. So did you have to look at any safety related factors for this?
I don't think we look too much into safety for this one. No.
So on the factory floor, many times we do design some automated equipment, and it is used in manufacturing, say, automotive parts. It's one of our commercial products as opposed to medical. But anytime an operator is getting close to a piece of equipment that has actuators, there are many times there's either a light screen or there are buttons that they have to hold so their hands are held away from wherever the actuators are. So there's things like that that you do. And so that is something that, you did not get those constraints as far as apparently for your project, and you were designing to meet some goals that were presented and the way you gave us that information. But a lot of times you have more than just those rather, not vague, but not too constrained type of specs. So I'm just kind of alerting you to that.
Okay, thank you.
Perry?
Yeah, sure. My name is Kerry Galloway. I work with Burns and McDonnell Engineering Company. We're most of the work that most of my background's in high voltage and medium voltage power transmission distribution. So kind of a wide range within that, from physical design to protection and controls to SCADA to protection settings. I apologize. I caught just the very end of the presentation, so I don't have a lot to contribute. I guess one of the questions maybe that I'll throw out there is, and maybe help me out, is this one of the projects that started with a previous semester's work, where basically you had to pick up where the previous semester left off? If I assume that's the case, Alan, I appreciate the head nod. I guess one of the questions that I have is, was there anything in that previous path that they had kind of established that maybe you would have done differently, or your starting point on that is not where you wanted it to be, or maybe it was presented as if it was further ahead than maybe it was?
Right. I think that, yeah, that's a good question. So basically for us, the way it was presented to us, we had touched on this a little bit earlier too. The way it was presented to us is that the previous senior design team was able to get their old gantry system fully functioning and working properly, and we that's like when we spoke with the previous senior design team, like they said that they have it all working basically, right? So coming into this semester, our first task was to basically run the system and make sure it works correctly, right? Just to be on the safe side. And it turns out that that wasn't necessarily the case, like especially with the vision system. It was having a lot of trouble detecting shapes and colors for the PLC code would run okay. But in terms of the vision system detection, we'd put an object on the belt and it couldn't recognize, okay, like, is this blue? Is it a rectangle? Things of that nature. So we really had to, or also it was very sensitive. Like we'd come in one day to work on it and we'd just turn the camera just a little bit and the whole thing would just mess up again. So it was a very sensitive system, and we had to kind of just work around that and figure out how we could get it to work correctly. And by kind of learning that vision system software, learning how it works and all that stuff, we were able to get that correct all the way. And then we could finally start working on, our new gantry system that we were going to implement.
Gotcha. Yeah, and I bring that up. I think we maybe talked about this with one of the other teams last week, was the super important in those handshaking between scopes of work, whether one person's taking care of, a piece that interfaces with your piece. You may not know everything that they're working on, but understanding what those guidelines are that you're working towards. And then certainly if you're putting a project down or somebody else is taking it over, that handoff is super important. That documentation on this is what we did and this is why we do it. And these are all the problems that we had that you may face. So don't repeat all those problems. So.
Right, absolutely. And my plan is just based on the last team's final report. Our plan is hopefully in our final report, we can obviously like reiterate any problems and stuff that we face so that there is going to be another senior design team next semester that will be taking it on. So hopefully if they run into a problem, it's something that's happened before and we have an easy solution for. So just so we could keep the project moving.
Yeah, the team work on this project last semester was the most successful one over the years. I think that, let me ask the question, what did you change that the last year the team can do what you failed to do this year?
So in terms of what we could have or what we were hoping to accomplish is obviously being able to test out our motors on the gantry to see like it actually moving physically. Obviously, because we ordering some of our parts from our parts suppliers, they had a lot of time to ship out to us, or it was going to take a while to ship out to us. We couldn't get to physically or mechanically build the system all the way through. So that I'd say that was probably like the biggest concern for us. But other than that, there's a lot of stuff in the PLC code that we had to adjust for the new motors. We had to make sure that the communication was working correctly with the OMRON motors compared to the microstep driver motors that the other gantry system used, and things like that.
Let me ask the question in a different way. When you get into the second semester, do you have your project well defined?
Well, actually, that's probably something that we needed to work better on, is coming into the semester, because obviously when working with the previous senior design team, we didn't know exactly how far or what the end result would be, right? So that's definitely one thing that we could have improved on, is figuring out once we got the end goal or the result of the last semester's team, figuring out, okay, what exactly needs to be done before the semester starts, because it did take us maybe a week or two to figure out exactly how we wanted to develop a starting point.
Yeah, sorry, I didn't mean to put you on the hot spot. The reason is no, the reason I'm trying to make the point to the industry advisory board members here, we have teams come to the second semester, the deliverable is not well defined yet after the whole first semester. That is something where I think we really need to improve.
Right,
okay, thank you very much. So that's why I did it for a purpose, not to harass you.
Yeah, no, that's okay. And it makes sense, because, you know, even you remember, Dr. Pei, when we met with you at the beginning, right? With Dr. Trombetta, all that stuff.
I remember all the discussion. That's why I'm trying to make a point.
Yes, sir. Yes, sir. Yep.
Okay, Team 6.
Dr. Pei, let me ask you a question before
Yes.
Team 6 starts. Did you give the teams instructions about, we're turning on the camera? I see some of Team 6 is turning on their camera. Did you suggest that they do or do not use the cameras in their presentation?
You mean to turn on their own, then we can see the speaker during the presentation?
Yes.
Okay. I think we have two screens, right? So one screen we have the all the people. Then we can use the gallery view or use the speaker view. I think when people share their slides, that's what we can see you now when you are speaking. Okay. What happened was that the last team just unshared their slides, so that's why we can see the people.
I think Team 9, none of the presenters in Team 9 turned their speakers on. We could not see their faces, and I'm asking that unless you told them not to.
I did not.
You're the professor. That I would request that you turn on your if you're speaking, turn on your camera so we can see your face. Thank you.
Okay, Team 6, would you please share your screen and turn on your camera?
Yes, absolutely.
Thank you.
All right. Let me turn on the slides. All right. Hi, everyone. My name is Hector Carrera, and we are Team 6 with the NASA TSGC Design Challenge for the Reconfigurable lighting system. And I'm Hector Carrera, as I said, I am the team leader.
I'm Chris McLaughlin. I can't really see the slides right now, actually.
Oh, okay. I may have shared the wrong screen. Just one second.
I can see the slide.
Oh, is it? Okay, I may have shared the wrong screen. Just one second.
Ah, there we go. That's much better.
Okay.
There you go. Perfect.
Well, I'm Chris McLaughlin, top right.
I am Christopher Andrew, bottom right.
I'm Jackson Clark, bottom left. All right, next slide. The background problem, the current lighting system used by NASA is bulky. It weighs about 9 pounds. It's not very efficient. It is based on fluorescent tubes. It's not very flexible. The fluorescent tubes don't have a dimmable setting, nor do they have any settings for the color temperature it outputs. It is fixed. It's not portable. It's kind of complicated. It requires additional circuitry to make sure that the current doesn't accidentally overcurrent the tube, and it's not compatible with circadian rhythms because it only outputs a certain spectrum of color temperatures. Next slide, please. Light is needed for workplace safety. Here on Earth, we have to worry about improper lighting causing trips and falls. But up in space, improper lighting can result in accidental contact with objects or work areas. And then up in space, it's hostile, it's isolated, and the ability to emulate the light cycles here on Earth could help astronauts be more adjusted. Next slide. The proposed solution is a portable lighting system that allows the user to adapt the light to their needs. It will have a controllable brightness, a controllable correlated color temperature, and if needed, they're able to upload their own customized firmware. Next slide.
We broke our project up into 4 major project sections: the physical shell of the device and structure, the electrical portion, control systems, managing batteries, the software portion, which is controlling the LEDs themselves, and then the user interface consisting of buttons and a USB port for charging. Next slide.
So before showing the actual design, we wanted to go over the requirements that we were trying to satisfy when designing this. We primarily focused around safety for enclosed spaces, like tight spaces like the space station. Our first major concern was the lithium batteries that would be stored inside of our device. According to some studies done in the Journal of Power Sources, there are concerns when using lithium batteries in certain vacuumous areas where the heat transfer is not quite the same as you would find in a normal atmosphere. But the overall article was positive towards lithium ion batteries. So this is why we chose the batteries of 18650s, which are commonly used in vape pens, surprisingly. But unfortunately, due to the lack of choice for consumer grade rechargeable batteries, these are the ones we had to pick. And they were the only ones that were acceptable for our battery life that we were trying to go for. Our second major concern was the printing material itself. The standard TPU used by most 3D printers has a reputation for not being too good against open flame in general and other heat-related problems. And with having circuitry and lights and batteries inside of it, we wanted to choose a different filament. So we ended up choosing PLA. This is due to its clearness, so we can get a lot more light out of our device. And some studies performed by the Polymers for Advanced Technology suggest that it is actually more flame retardant than most other 3D printing materials. Next slide, please. another one of our concerns was charging our batteries properly. We don't really want to test how flammable our PLA is by blowing our batteries up inside of the device. So we chose using a battery management circuit module to ensure that our batteries are charged properly. Due to the configuration of our batteries being 4 cells in parallel or in series, it was difficult to find a proper battery management circuit, but we ended up finding one at the end. Finally, we wanted to make sure that we produce enough light for working in a safe environment. A study done by the Journal of Ergonomics suggested that in hospitals, the minimum lighting requirement for a safe working environment was 93 lux. So that gave us kind of a baseline brightness that we were trying to achieve. Next slide, please.
So for the deliverables of the lighting system, we were tasked to deliver 3D models of the lighting system, as you can see here. So we decided to make an orb and to encapsulate all the electronics inside the orb inside a pole. And we, of course, needed to develop some software to control the lighting system. And that involves electrical diagrams as well. So we had to do all of that, the development, and that combined are all the deliverables. So for our specifications, we had minimum viable specifications before the second semester started. And we actually exceeded our specifications in a positive way. First of all was the brightness. So minimum, we had it to where it steps from 100 to 1000 lux. We were tested to having obviously color temperature control, brightness control, 5 hours of battery life, the 3D printed shell which diffuses LED light, USB charging, and the magnets as the mounting structure. But we did exceed the brightness by up to 40% at 1700 lux. And we had wide-ranging color temperature control from 2400 to 6500 Kelvin. And we had we almost doubled the battery life at 9 hours. So we did exceed those specifications. So that's very positive. Let's see, next slide.
So as shown in the deliverable slide, we had the 3D models, but the actual structure of it came out to be a spherical object that's mostly clear, that came out to be around the size of a little bit smaller than a volleyball, which I know is a weird unit of measurement. And it was broken into 2 major parts. The left picture showing the mounting post, which included a hollow compartment for our circuitry. And then it also provided a point for us to mount the LEDs on specifically. On the bottom of the post, as you can see on the right image, we actually had multiple ports for the buttons, switches, USB ports, and 2 threaded holes that allowed for the 2 parts to screw together. And then partially visible on that image is the actual sphere itself. The reason we actually chose the sphere is we kind of wanted to have a sci-fi aesthetic, I suppose, and we thought it looked quite nice. Next slide.
At the heart of our system, the light is provided by 2 LED strips with correlated color temperatures on opposite ends of the spectrum. Those LEDs are driven by 2 common source MOSFET amplifiers because the output of the TIVA-C microprocessor voltage is not enough to properly operate the LEDs. And for our controls, we have, like I said, the TIVA-C that is controlled by 2 buttons that are momentarily switched. And then this whole thing is powered by 4 3.7 volt batteries in series. And to ensure that we properly charge and discharge them, we have a battery management system which checks on the voltage and the current going through each individual battery to ensure that neither battery is overcharged compared to another battery. And then in order to get the 2 operating voltages, we have 2 step-down regulators, and that's the bulk of our internals.
So now we're going to show you a very short demo of our project in action. So in this first video, we're going to show you the LEDs or whenever we press the button underneath the orb, we can see the LEDs just stepping up and down if you hold the button. And then in this next video, we're going to show you the just one second. In this next video, we're going to show you the varying color temperatures. So if you press the other button, which we showed earlier, it actually switches from the 2 LED strips to give you either a cooler or warmer tone. And we obviously have the switch to turn off the orb as well. Okay. So in terms of accomplishment, like we said earlier, we exceeded our initial specifications in terms of battery life, brightness, and in terms of features, we did include more features than we expected. And we believe we created a relatively minimalist design and efficient circuitry for this project to achieve that accomplishment in battery life.
For setbacks of the project, we had 3 major setbacks. The first was a redesign of the post. Originally, we had a solid cylinder and we were planning to mount electronics at around the base of the cylinder. This did not provide enough space. So we swapped to a hollow cylinder with the lights mounted on the outside and all the electronics stuffed in the middle. The second setback was the voltage regulators we're using to power the TVC during startup can damage the TVC. We fixed that by adding voltage spike protection. And the third issue was our battery charging system during startup drew more current than it should. We fixed this by adding circuitry to limit the max current draw of the system. Next slide. For future plans for this project, we're considering Bluetooth controller, 1 or more units, swapping from USB 2.0 to USB-C to allow much higher power draw for a faster charging time, and all-in-one PCB design. We're also looking at 24-hour color, temperature, and brightness profiles so it can set up and it will just automatically change over time. We also wanted to move to a different 3D printing process to produce a clearer sphere. Next slide.
So in terms of lessons learned, the most important one that we learned was the engineering design process. And with that, specifically organizing and delegating tasks. That was something that they would definitely struggle at the beginning of the second semester. But over time, we definitely got to optimizing that. And obviously handling the setbacks, which we already mentioned, the 3D printing, the voltage spike protection circuitry, and the USB communication, which ended up being more complicated. Those were all lessons that we learned in the future for engineering design. So in summary, we believe we developed a robust, minimalist, functional, and reconfigurable lighting system for crew in outer space. We completed the project under budget and ahead of schedule. And we believe we fulfilled all the tasks related to the project. And we learned a lot from the setbacks, the challenges, and the intricacies of engineering design, and the importance of keeping a schedule. So we believe we learned quite a bit from this project. And lastly, we just want to thank our mentor, Dr. David Marriage, and our project manager, Dr. Pei, for helping us throughout this project and throughout the semester. And with that, we're going to hand it over to some questions.
Thank you. Tommy, would you go first this round?
Sure. So I thought I heard you say that y'all chose the 18650 batteries.
Yes, that's correct.
So did you choose the ones that already had the safety features on the battery, or did you choose the ones that are just basically the cell?
We selected just the cells, and then we developed all the battery protection circuitry on the side. Yeah.
What protection did you put in?
Jackson worked a lot on that. If he can elaborate on that.
We have regulators. We have arrangement that makes sure that the batteries aren't overcharged to where if it reaches past 3.7 volts, it will quit charging that battery cell. And then we also had protection to make sure that no battery had more current going into it than it could handle, or if that battery is already charged to the max, that it wouldn't be getting any more current into it to charge.
Okay, so there's a couple other things. So you did cover the overcurrent and over voltage. How about over temperature?
So over temperature is something that did cross our minds, but we didn't quite consider with this project. We definitely did do, like, in operational states, we did measure how hot everything got, and the thermal output out of the whole project is not very high. It doesn't get warmer above 85 degrees or so. So but definitely, I guess, like, in different environments, we definitely could have taken those into account into the thermal design for sure.
Right. I mean, I'm asking you these just to kind of see how far you took it. I mean, the fact that you did do the overcurrent and the overvoltage, those are good starts, and you're aware that those batteries have limitations.
Yes, of course. Yes.
And there is actually an over discharge aspect of it too. You don't, for lithium batteries, you don't want to over discharge them either. So that's kind of where I was headed with some of that. You can buy those batteries. They're a little bit longer than just the regular ones. And they have a number of those features already built in.
Okay.
Yeah.
All right.
So you could have just used those, and it might have saved you a little bit of harassment on that.
Oh, okay. All right.
So I'm actually using 18650s on a portable device I'm designing right now. So that's why I'm familiar with them. One of the things I didn't see was charge time.
Yes. So for charging, when we're doing our testing, it took around 2 to 3 hours to charge. So we definitely, like we did mention in our presentation, I forgot which slide it was, but we did say that if we moved over to USB-C, we could have charged at a higher wattage, which would have
Right. I remember that. I noticed that. But where I was headed was, what is your requirement for charge time? Do you need to be able to charge it up within a certain time? Like oh gosh, I only have about an hour to charge this between uses, that type of thing. Did y'all have any constraints in that regard?
So that's something that we definitely should have looked at. We initially just deduced that if it takes around 2 to 3 hours to charge, that would have been okay. But we definitely should have added some constraints and have had a specification for charging for sure. Yes.
Yeah, I understand. So I guess one last thing was, when you had the overvoltage with the buck converter, how did you solve that problem?
All right, I believe Jackson, you can help me.
The over voltage for the microcontroller.
Right.
Yeah, we solved that problem using a Zener diode, a 5.1 volt Zener diode, and that seemed to solve all our problems. We weren't really exactly sure why we burned out those TVCs. Like Chris Andrews said, we believe it's a overcurrent spike that was happening from the step down regulator.
Yeah, a lot of times, so you were trying to be efficient and maybe using a switching regulator. Is that what you're using for the 5 volts?
Yes, sir. We're using a switching regulator.
Right. So you would have had, now your 12 volt supplies all the main power, right? That's where your current draw is, right?
Yeah, that's for the LED to operate properly.
Right. So on the 5 volt side, I mean, it's more efficient to step it down with a switcher, but you could have just used a low dropout regulator for that. And then it was just it's just a linear drop from your 4 battery voltages down to that, if you're drawing low power on the other side of it.
Yeah, that is true. We could have done that. I just remember reading about different power circuits when it comes to rail splitting and which one's more efficient and which one's not. And
more efficient, yes. Sometimes what I do is that regulator where your 5 volt is, I'll take that to 5.5 volts and then put a low dropout regulator past it.
Ah, yeah, that
You
that
see
would have
that?
worked.
Yeah. Okay. Anyway, I just had a few technical questions. This is pretty neat. You did good stuff. I like what you did. So
Thank
Yes,
you.
years as of experience here. Carrie, would you want to be the next one?
Sure. Yeah. Just one question. Maybe I know you put up your original specifications and you indicated that you exceeded those in several, specifically like on the battery life, you exceeded, I think from a space perspective, I think maybe the bigger concern is, how much weight could you save if you didn't need your specifications designed to that level where, maybe cost isn't the biggest consideration, but maybe weight is. And then maybe on the kind of in a different marketplace like manufacturing, you may be more concerned about cost. Like if you were designing something very similar, but where scale would eat you up on cost. Kind of leading into the question that I have is, what things would you change in your design to dial back to what your minimum viable product is in order to reduce cost or reduce weight in your design?
Yeah, absolutely. So the biggest portion of the project that uses the most weight is the batteries. So I guess making just everything even more efficient, or using more efficient hardware, or integrated, or using the batteries like Mr. Cooper said, that already have that battery management system built in, that could have definitely saved a lot in terms of cost and weight, which is very important in outer space for sure. And also maybe made the project a little bit smaller, so that way that in turn also reduces costs and also reduces the weight for sure.
Gotcha.
Okay. Alan, we're saving you for the last.
Yeah. So, and my question was around the same slide here. You've got 2, 4, six. There are 6 or 7 specifications. Listening to you talk about your project, it sounded to me like your client, which is in this case is NASA, didn't give you a lot of tight specifications. Your response was, yes, we should have had a better one of those, or we should have thought about that more, which means your client didn't tell you exactly what he wanted. Now, I bet Tommy would say, because Tommy works with lots of different clients and they don't always know what they want. So part of his job is to go nail down before he starts working what they really want. And so it looks like you've got an example of this here. They gave you some specs. They probably care about a lot of other things, like that battery. You said you chose lithium ion, or after reading a paper, or considering some safety issues. I understand there's lots of it because of the energy density inside that battery. There's lots of safety issues with lithium ion, and I'm surprised NASA wouldn't have given you a requirement. It either can't be, or it must be, or something, because of the safety of the devices that can't explode. Explosions are bad. Explosions can be catastrophic in space. So it sounds like this is just one of those examples of the client didn't really give you a comprehensive list of what you needed to do, and so you filled in the blanks. Well, in the real world, of course, you'd have to go back and review each one of those with the client, or you get to the end and he'll tell you, wait a minute, I can't use that, or it had to do this, and he never told you that up front. So real world, get those specifications completely nailed down, or as much as you can up front, so there's no surprises when you get to the end.
Absolutely. You're absolutely right about that.
Yeah.
Yes. Mm-hmm.
One of the arts to consulting is you have that session where you listen to the client and have an hour or 2-hour meeting, and you're going over all the aspects of the project. And then you've got to boil that down into that specification and send it back to them and see if you hit the mark. And yeah, you're writing the specs. They want specs, but they can't necessarily spell specification. So there's that. And then there's those clients that bite you tooth and nail. I've had it take a year to get a specification agreed to, a year into the project. and others of similar ilk. There was one project where I was on version 15 of the product specification. That ought to tell you something. It failed.
Wow.
Yeah. Well, thank you for this discussion. I think that we went over time, but you control your presentation time very well. I don't want to cut the discussion short. So that was not your fault. I think credit to you, you control your presentation very well. But I want to give you the full benefit of discussion with our IAB members. So the next one is Team 10. Go ahead. So don't forget to turn on your camera and share your screen.
Hello. I won't be able to share my camera because I don't have one, but
okay.
Hopefully my voice is nice enough.
Just getting all set up to share our screen real quick. Okay, let me put that in full screen. All right, can you see everything okay?
Yep.
All right, awesome. We'll go ahead and get started. Hello, my name is Justin Flores. I'm part of the Team 10. We are doing the high resolution 3D scanning presentation. Our faculty advisor was Dr. Reddy and our project manager was Dr. Pei. I'm the team lead for this project. We also have Rodrigo Mascarenas, David Salazar, and Daniel Rodriguez working on this team. So for our agenda today, we'll just go over the background and problem statement, our motivation for the project, followed by deliverables and features, in which we'll touch a little bit on engineering specs and our test plan. And then we'll discuss our project status and results, including accomplishments and some setbacks over the course of the project. And then we'll end with a brief summary of some of the lessons that we learned from the duration of this project. All right, so our purpose was to essentially bring medical grade high resolution 3D scanning technology, which is readily available, and be able to scan larger size objects with interferometer setup. Other methods of 3D scanning do have drawbacks and benefits. However, we kind of wanted to bring a full package to the market, or at least show a proof of concept for that. Things like manual 3D modeling can be very time consuming and tedious. LiDAR can be processed quickly in low resolution, but as you scale that up, it becomes much more expensive. And things like photogrammetry are meant to be used for large objects or large areas, and it provides a lower resolution.
So for most high resolution 3D scanning, they reach a peak of resolution of millimeters, which is somewhat expensive, and their setup is limited to not millimeters to meters of the object scale, whereas our setup will have the potential to reach a peak resolution in a micrometer scale. It is adjustable. It is adjusted to be more affordable to fit multiple budgets, and then eventually be scaled to have the flexibility for the scale of object scan in the range of micrometers to meters. So this is our micrometer interferometer. This is our microsync interferometer setup. It has a potential to be miniaturized, and depending on the object scale for the consumer is looking for. We wanted the project to have high accuracy and use inexpensive equipment to prove that we can have a good quality 3D scan. So for our specs, we wanted to be able to scan objects from micrometer up to the meter scale. We wanted to be in between working temperatures because outside specs will create distortion or noisy data. And the frame rate, the importance of the frame rate is to improve the data capture that is specific to the final asset. Here is we have our overview diagram, which is a visual layout of our setup. And the interferometer setup, it includes laser, the beam splitter, mirror stage, high-speed camera, and the object that we are scanning. This from there, it talks back with the lab view control, so which makes it autonomous, and it will move. From there, we'll move from from the to the MATLAB for data processing and image for data processing, which is image processing, and then it will output from there. After the code runs, it will output a 3D scan.
So to begin our project, all four of us were new to optics. We initially started with this project build. So most of the components were we picked up a project that was initially had been ran and they had some results, but we picked up on their project, and to begin with, most of the components were actually parted out. So as you can see in our flow chart, our first task was the toughest to get started due to the fact that multiple components missing, shipping delays. But we even though we had those obstacles, we took advantage of the time and by researching and getting familiar with optics. We had a couple of classes with the grad student that Dr. Reddy assigned to us to help us out understand and how to approach our project and obviously our task. Then we proceeded to obviously the setup, getting familiar with everything with task 2 and task 3, which we will expand out. My teammates will expand more as we go through the presentation. So here we have our test plan. We divided our approach on, these are certain subtasks, the critical subtasks that we had by functionality, testing parameters, verification method, and target values. The two most critical to get this project going was the first one with the interferometer setup, getting the actual camera to actually scan and reflect back to what we're getting actual images so we can then process. So we hit our target value for that one, and as well as the autonomous lab view, we also hit our target for that one as well. But these are subtasks that we'll jump in and expand more on our following slide. Here's our Gantt chart, kind of each subtask on the left, how the progress over as we achieve throughout the semester. Within mid-September, early October, we finally received the camera after reaching out to multiple vendors, reaching out to our professor to see if we can get a camera expedited to get some sort of results going. Once we received our camera, that's our first milestone that we accomplished, to have the camera working, then learning how to actually get all the setup going, and to then proceed to milestone 2 and 3 as we progress through the semester. On the right, we have our, like I said, our milestones and how we accomplish them throughout the semester. Here we have our most recent interferometer setup, completed with our new Basler camera and functioning motor controller. We made incremental adjustments to improve the setup, including constant realignment and correcting the reference mirror distances to prepare a better image output for later so we can analyze. We also utilize a beam expander consisting of 2 lenses before the splitter to increase the scan size, and the ND filter to reduce the overall exposure of the recombined beams so that the camera sensor could record the data without issue. And that's how our setup is. As you can see, that's the laser, and on the top left we have our output or power modules. It has a temperature control on the actual laser that powers it up. That's our general layout as far as our actual scanning that we have for this project.
All right, so this is what or partially what the user would see. On the left side, we have our LabVIEW virtual instrument up to the most recent one that we had. And this can be customized based on the user need. On the right side, we have the block diagram that kind of controls all of the motor control, the image acquisition, and then the data output as well. And I'll just show a little bit more of the block diagram. There's a couple of loops in here, a little bit more complicated than we need at the moment, but all that to say, essentially what it's doing is it's taking an image, using the the motor control to first hone automatically, and then what it's doing after that is utilizing the images that it's exporting in order to basically export data every time the motor is moving over a set period of a set distance. So that way we can process that data after the fact. As a test, I had this one to basically export an image data with the name, with the title, with the distance that the motor had moved. As you can see, even over a course of just a few seconds, it exports a ton of images. And this is why we needed an updated camera. The previous camera that we were able to set up did not have the ability to scan at a very high frame rate. This allows us to, once we were able to upgrade, we were able to get a lot more data from the same period of same distance moving. So that way it was, we could find a little bit more information there and be able to interpret that data.
So this is what it looks like after we combine all the pictures. As you saw from the previous slide, we output a lot of pictures, which is exactly what we want. And if you look carefully in the image on the right, it's a moving picture. It's a GIF or a GIF, depending on how you like to call it. But the point here is that we're able to capture exactly how the interference pattern fringes, which are those dark blacks and bright whites, and how far away they are from each other. And that's how we're able to extract the information we need to create a 3D asset with depth information about the object. So from there, as soon as we collect all the images we need, we're able to use our MATLAB program, which basically takes an input as the sequence of images that we generated. And then it performs a series of operations on the images, from anything from normalizing the data, taking the Hilbert transform to extract the phase information, which is used to generate the depth information. And all that, after all that happens, we are able to generate a point cloud of the scanned object. And from the point cloud, we're able to clean it up a little bit and create a polygon mesh of that data, which eventually becomes the 3D asset file, which is our output. Yeah, I mean, the digital processing, we eventually want to move that to the cloud so that we're able to free up any operations from the interferometer setup and basically delegate the image signal processing aspect to the cloud so it can be processed over there. So in terms of results, setbacks and accomplishments, like we previously mentioned, we had a lot of problem getting components that we needed. So that did impact our project a little bit. We tried to plan as much as we could, because that was kind of something everyone saw it coming. If you had shortages of cell phones and cars, can you imagine expensive lab materials? So we knew that this was coming, so we were trying to plan as much as possible, but it still impacted our project in a way. As well as our setup, we were sharing a lab, so a lot of times our components were being used for different projects. So it took a lot of time to be able to reconstruct the setup every time that happened. And other administrative issues that we faced, but once those are cleared, we had the lab to ourselves, and we could work on it as much as possible. But now, in terms of accomplishments, we're able to set up this interferometer device to anything from aligning the mirror components and making adjustments to the setup itself to improve our data capture. We're able to completely from scratch create a lab view, front end and back end, to control this hardware and be able to process this image, although still in progress, process this image and eventually be able to get the 3D asset files. And I guess it's worth noting, none of us had any background in optics apart from physics 2 class that we took some time ago. So it was a pretty interesting learning curve, and we definitely learned a lot during this project, which in itself is very rewarding. And in the summary, from the issues we had, like I said, it's very important to be able to work around these things. You might not necessarily have the equipment you need at all times, but you want to try and make the best out of the time and the equipment you have, and try to take advantage of that instead of just sitting and waiting. And the proper alignment of optical components can make a really big difference. I cannot stress this enough. And having documentation is very important. This is technically a continuation project, but once we picked up this project, we didn't really have anything to get it started with. So one of our goals was also to leave a lot of documentation behind so that future students can pick up from where we left off and not have to kind of like reinvent the wheel. And of course, we all had to learn LabVIEW and MATLAB to be able to integrate those things together. And cannot stress enough, optics is hard, but I think we came a long way. That pretty much sums it up. So we'll be open for any questions you guys may have. Thank you.
Thank you. You just did it within the schedule. So Kerry, would you be the first one this time?
Sure. Yeah. So one of the things I guess I heard a lot about the setup of the tools and the kind of the processing of the actual data that you were collecting. One of the things that I didn't hear that I listened for from the very start to the very end and I never heard is I never really heard about the application of this. I don't know who your target market is. I don't know who your customer is. I don't know what you would use this for. And while maybe if I was sitting here and I was super familiar with this process, then maybe that was intuitive. But that's one thing that I don't understand that I'd like to hear from you on kind of, you've worked with this, you came into this. I assume that when you started this project, you're probably like me, you didn't know what, interferometer was. Maybe elaborate a little bit on what the application of this is at this scale, right? So I understand 3D scanning. We use a variety of different 3D scanning techniques now in high voltage transmission for design, integration of, brownfield applications. So that's one piece of it. Then I had one follow-up question, maybe after you touch on that.
Sure. So as far as the purpose and the kind of motivation of the target user, we found in our kind of our research that there was a lot of different kind of target markets, whether it was highly technical, creative. There was a lot of applications. However, we didn't want to dive too deep into every user base. We did just mention the different methods of 3D scanning that somebody may previously take advantage of, such as the LiDAR scanning, the 3D modeling from scratch and things of that nature. So somebody typically associated with those methods would be able to benefit with the increased resolution if they needed it.
Yeah, so I was gonna say, give me an example of somebody who needs more resolution than millimeter to micrometer. I'll say this, just because you can doesn't mean you should, right? When we work with our designers and our engineers, and just because we can, put level of detail into a deliverable doesn't mean it's necessary. So, that's one thing I would maybe just kind of caution you on. Just because we can over-engineer something doesn't mean it's economical or that there's a customer for that. And certainly, one of your selling points on the front end of this was cost competitive. Don't always assume that price is the motivator, especially for something super technical or something that pushes the bounds of the resolution from millimeter to micrometer. If there's an application where, I need this level of resolution to, for quality control on some, medical device or whatever it may be, where, cost may not be the biggest driver there.
That's
go ahead.
Oh, sorry. Yeah, that's a very good point. So our idea here, obviously this is not a finished product. What we hope here is to bring a different approach to this field and really bring an enabling technology that can be used for various applications. And coming to what you said, I 100% agree. Just because you're able to get to a micrometer, do you even need micrometer? A lot of times these applications, you don't even need that. So what we were trying
So
to show.
another thing that Dr. Reddy kind of talked to us when we met up about this project was the approach that this was a typical like medical application where you want to actually scan to detail for medical, maybe for any outputs or actually printing out or trying to get a good detail of a certain specimen that they're trying to scan. So our application or his idea was to make this a more usable, user-friendly for if the need be to duplicate or copy such scan or certain device to maintain quality. Some of the things we saw were like maintaining some of the historic scans of quality of getting even to the texture point if need be. But that was kind of like a background towards it.
And then just one real quick follow-up question. Because you were scanning at that low, that super high resolution, did you have any issues with stabilization of the equipment? I would be concerned about an air conditioner running in the building if I'm trying to measure at that level. So I just was wondering if you ran into any, stabilization concerns related to that area.
Yeah, I think David can probably speak to that.
You can go ahead.
Oh, sorry. I was saying you can go ahead because you actually experienced
that.
With,
so the setup more than anything, while we're setting up, the grad student kind of did tell us, hey, temperature, vibration from the AC, anything you will read it on the actual fringes. Another thing he said, even the automatic platform that we're moving back and forth, the vibration itself on the actual table would actually produce would actually affect our actual scan. So there's a lot of factors that can actually contribute to lowering our quality or accuracy to our actual scan. So those things we had to we could only limit them to a certain extent. But yeah, that's the one thing, some other stuff that we actually were looking out for.
My turn?
Yes, Alan, yours.
Yeah, my first comment is that some of the same education you needed about optical systems and how an interferometer worked probably would have been helpful for this audience here. And so that really the broader, and this is kind of a mix of skill and art. Whenever you're making a presentation, you've got to understand who you're talking to, because if you talk over their head, their eyes glaze over, and if you too elementary, they'll yawn and go to sleep. So you've got to understand who you're talking to. So you're here, if you're talking to Dr. Pay, you're going to get one thing. If you're talking to industry advisor people, they're working engineers, but not necessarily in this field. So I don't understand optical interferometry. So that would have a little bit, one slide background would have helped. So know your audience and understand what you need to educate them on and what you don't. I didn't see, I just missed it, that you tested your final system to show that it met the requirement that your, I guess it was the other professor you mentioned, I don't know him. Did you demonstrate that you met the requirement that was given you?
So I believe that as far as meeting particular milestones on the different tasks that we kind of had the entire project built up into several different tasks. He also kind of understood because he was kind of on the forefront of ordering some of our equipment, and he actually provided a lot of the components, or pretty much all the components that we were using, although those were being shared between multiple grad student projects and such. We basically broke it up into different groupings of tasks, which was the setup and the alignment, followed by the image processing and data the hardware control and the data export, and then the third was going to be the actual image processing into that final file that would be used by the end user. And we were able to actually multiple times able to reach that milestone, that initial milestone of the setup, as David and Daniel mentioned, those from semester to semester, that was unfortunately disassembled due to the nature of having shared parts in a shared lab. So it was a setback that we had to deal with. And then additionally, the camera arriving late, the intended camera, unfortunately used a completely different interface with LabVIEW. So just because we had one working previously doesn't mean that we had that we couldn't. It wasn't plug and play with the second camera, the better quality camera that we were able to use.
So
but we
let me interrupt you in the interest of time. So your output was some kind of an image file, a description of the thing that you had scanned, correct? Is that correct?
That was a target output, yes.
Yeah. So how do you know that the output that you generated really matched the object you scanned? You could generate a scan that didn't really match to within a micrometer of the real thing. How do you know that the image model that you built was accurate, that you did what your sponsor said he wanted you to create something useful that worked, not just that worked, but worked accurately, worked well enough?
So our sponsor actually, Dr. Reddy had said that the initial part of the project was to essentially create something that works. Just first and foremost, create something that works and is able to scan information. And then from there, we can iteratively increase that resolution, because that he did say from the outset of this project that the setup and the initialization of that hardware control was a lot of the project, close to 75% of that project. And so
did he reference model or something? So scan this, and I know what the image is supposed to look like. So if you give me some other image, then I'll know you did it wrong. But if you give me this image, I'll know you did it right.
Yeah, he didn't give us anything specific. It was more so like kind of a target that we would hope to achieve eventually. And he did also mention that this could be something that is continued in the future if we were able to get that set up and get the initial LabVIEW work kind of outset for a continuing team. And I feel like we were able to accomplish a lot of that. But he didn't have anything too specific. He did show us some examples of smaller objects that could be scanned and an object scale. He said something along the lines of, something a bottle cap size up to an apple would be the eventual target. However, he did say that this is sort of a proof of concept that a system like this could work.
Okay.
Thank you. Any more questions? Okay, thank you for the comments from the IB members. So the next one is Team 2. So Team 10, you can unshare your screen. Team 2, are you here?
Yes, sir. I'm sharing my screen right now.
We're waiting for Alex.
And all members turn on your camera.
Okay, can everyone hear me?
Yeah.
Yes, let's go.
Okay. Hello, my name is Faiza Badapura. Joining me are our team leader, Alexander Crisco, Christopher Frank Lamont, and Gantabia Cadell. Our faculty advisor was Dr. Hong Lei, and our project manager is Dr. Pei. Our project is Smart Engineering Building, and we are developing the Smart Building System. To give you a brief introduction of what we will be discussing in our presentation, we will be going over the background of our project, the deliverables of our project, and then we will go over the results that we obtained and give you a short summary. So the broad problem is climate change and energy consumption. Greenhouse gases from energy production are a large contributor to climate change, the main issue being a 2° Fahrenheit increase in average global surface temperature. Specifically, as we can see in this diagram, heating, cooling, lighting, and appliance operation contribute to almost 40% of energy consumption in the United States. Our project uses IoT sensors, which are used to create an automating control system containing a HVAC system and a lighting system to reduce energy consumption, which will be explained further in detail in the presentation. Our project goal is to design and implement a microcontroller system that utilizes various data input devices, which are our sensors. Our system uses these devices to monitor real-world variables such as light, temperature, and motion. And our system intelligently and efficiently manages heating, cooling, and lighting systems of a building and gives our user flexibility and control.
So before we went into detail about our project, I wanted to give a brief high-level overview of how our project kind of works. So essentially our data gathering unit has edge detection and it has a timer. The timer controls the temperature readings, and then our light sensing and motion sensing circuits are edge controlled. So when these edges happen or the timer elapses, we send this data to our central hub where everything is stored. And then also on the other side, we have a website and a database that the users can log into and see the metrics that are happening in real time. And then they can also put in their designated max and minimum temperature. And then this is all sent to the data hub where the processing happens. And if you look at the bottom, if the preferred temperature isn't in the designated range of the user, obviously the HVAC turns on or off. And then if motion is detected or the lighting threshold is below what the user wants, then the lights turn on or off depending on what's happening.
Okay, now to discuss the deliverables of our project. So we identified first a couple of very important key features that our project needed to have. So for first of all, it needed to be completely modular, since you're going to need one central data hub per building and one data gathering unit per room or hallway. So each of the DGUs are going to contain all of the sensors that collect the data. Ultimately, that will be displayed to the user and used to automate the control of the building. We needed it to be as low cost and low profile as possible, so it can be implemented anywhere in any building, and also installed permanently or non-permanently. So for power, the data gathering unit, since they need to be remote, need battery power. The central data hub would be hosted on some sort of computing device or cloud computing service. So it's always going to be powered from the wall. And we wanted compatibility with any device that can access the internet, so the end user can use whatever they have to operate our system. And we needed it to automatically and intelligently control the building, lighting, and HVAC systems with the capability for the user to configure and override the system. And finally, we needed a web server interface and database to store and process all of the data as much as possible for the system's functionality. So our project used a couple of different microcontrollers. For the central data hub, we used an ESP32 for our control board and a laptop to host the servers. An end user could use any dedicated computer or cloud computing service instead. Data gathering unit used a TIVA-C and an ESP32 as well. It uses low power 3.3 volt microcontroller systems for the data gathering unit, so they use as little power as possible. We wanted high sensor accuracy, and these values were all verified. For example, the temperature sensor had plus or minus 1 degree Fahrenheit accuracy. We verified using a thermometer. The light level sensor, we wanted to have threshold detection of 50 to 150 lux, since this is the lower level of what's agreed is a well enough lit room for reading. And the motion sensor, we needed detection up to 20 feet, 120 degree cone of vision, and we mapped that out in real space. So right now, it has an operating time of about a month, since each of the 3 sensors and the 2 microcontrollers draw about a milliamp each. So for a 4600 milliamp hour AA battery pack, that would give about a month of runtime. The wireless communications all use 2.4 gigahertz Wi-Fi through the 2 ESP32 modules that we use. And we needed greater than 95% communication accuracy, can correct system operation 90% of the time, and at least 99% data processing accuracy for the system to be functional. And that's what we ended up with in the end.
Okay, so in the next few slides, I'll talk about the end user interface for our project, the website. First off is the login page. I like to call it the Cougar login because, it's quite appropriate. So our project comes with 2 predefined authenticated users to make sure our system is limited and sort of more secure. Next slide. So this is our home page, which is also the bread and butter of our project in terms of user interaction. In here, you'll see a banner with the weekly weather forecast, and in the middle, you'll have two partitions where you can see the current building temperature as well as edit temperature settings. On the left-hand side is what you will see the current indoor temperature that is passed by our temperature sensor, as well as the maximum and minimum indoor temperature settings that are currently on. And on the right-hand side is where the user will go on and change them as they like.
We also have a simple about page, which allows the user to easily learn more about our project and contact the team members should they have any questions, concerns, or comments. There are also contact buttons, which can help the user to easily connect with just one click. And there's also a brief description of our project at the end of the page.
All right, so in this, I'll talk about our systems operation illustration. It is similar to the overview that Alex just talked about, but in this one, we're talking more on the device level. So we'll start with the data gathering unit. It is comprised with our sensors and the ESP3232UE, which is our device A for I2C communication, and the TVC, which is device B. They're all supplied by a 4.5 volts 3 AAA battery. All of the sensor information goes through the TVC to the ESP32. Only the temperature sensor requires ADC, right? And the ESP32 then talks to our web server through a post request. It's an HTTP post request because we don't have the certification for the encryption with the HTTPS. And then the web server will then execute a query to enter information into our MySQL database, and then also render the new data into our homepage. And then finally, we have our second ESP32, the ESP32C3. It periodically sends the HTTP GET request to the web server to get respective flags to drive out outputs for the room light as well as the fan. And in here's actual DGU setup. It's sort of loose right now, but we'll start with the battery pack and the boost and the buck converters. And then it's the temperature sensor, the light sensor, and the motion sensor, which was on the white one. I don't know why the box is not there, but and now it's the TVC and the ESP3232UE, device A and device B for the I2C communication.
So we wanted to do a demonstration about how our system actually works. And I'll talk through the video as we go through. So right here, we are logging into our website. And this is the portal for the specific device.
Alex,
I'm sorry, what?
You're only showing the presentation from my end. So.
Oh, we are? Hold on. This maybe? Does that work?
Yes.
Okay, sorry. Okay, so we're logging into our device portal right here. And this is our home page. So you can see the current building metrics. We're going to specifically put the metrics, the current metric outside of the designated metrics to see that the HVAC doesn't turn on. As our little enclosure we made to test it. So the fan doesn't turn on. So the metrics are outside of the designated range. And then we change it to purposely make it outside. So the fan should turn on. And it's on. So it's working correctly. And then this enclosure also simulates a room with like a window on the sensor right there. So when we cover it, the light should turn on because the light threshold is below. And then it should turn off after a duration. And then the light, we try the motion sensor right there, and the light turns on, and then it turns off after a duration. That's it for the demo. So setbacks, and this is also advice if there's like a possible future team that takes over for our project. One of the things that we had issues with the TVC was using actual edge triggered interrupts. So I had to basically, the temperature sensor is on a 1 minute timer, but the other sensors, the light and the motion sensor, are on a 10 millisecond timer. that picks up the edges. So I basically pseudo edge trigger. So maybe the next team could do that, actually have interrupts that are edge triggered. And then you basically could remove the TIVA-C altogether from the DGU, because essentially what we used it for was the ADC, because the other microcontroller that sends and receives data from the website has kind of a bad ADC. It's not very accurate. So that's one thing that we could change. Also, we didn't use a PCB for our sensors. We wish we would have, but we didn't really have time to do it. But this would have greatly reduced the size of the DGU. And that also comes into play when we're talking about making an enclosure. That was one of the other reasons why we didn't make an enclosure for our system, because the jumper wires were a bit too high in terms of dealing with the light sensor and temperature sensor. So there was no way we could accurately make a nice enclosure for it and have the sensor stick out enough to be accurate. And this was due to just time constraints. And I'll hand it off to Faiza to finish.
So some setbacks for the website development was an ad hoc basis development of the database design. And there could have been a more efficient ways of doing this since we kept coming back to the same design after certain developments. And lastly, redesigning the web pages, which took time, but it was necessary for the website.
Okay, so in doing this project, we learned a lot of valuable things about projects in general, but also things that will be useful in our future careers. First and foremost was the communication between the microcontrollers. We use both I2C serial communication, also the Wi-Fi communication. Implementing the microcontrollers was a good experience because we got both a high and low level experience. The TIVA-C, for example, uses Code Composer in C, whereas the ESP32 uses the Arduino IDE and its associated language, which is much easier to develop for. We got to actually design and prototype our own circuits all the way from the ground level, which included researching the parts, reading the data sheets to figure out that everything would work together, and then physically assembling it. We used a lot of different coding languages and IDEs, including Node.js, JavaScript, and MySQL for doing everything involving the website and the database. We learned the basics of database management and the utility of it. We also learned through both the semesters of this course several important things about project management, including patent research, Gantt charts, risk management, and also writing reports and giving presentations such as this. We learned the importance of communication between team members. And finally, we learned the importance of sticking with the project, even when setbacks happened that were somewhat frustrating, to end up with something that at the end we could be proud of. And while we achieved only about 90 to 95% of what we originally strove to do, we're still happy with our final outcome.
And that's it. We'll be taking questions now.
Thank you very much. I think we're back to the beginning of the cycle. Alan, do you want to go first?
Yes, absolutely. So a high level question here. It seemed, so you started out talking about the problem of global warming and CO2 affecting the environment, but you seem to skip a bunch of steps to get to the project that you came up with here. So I didn't see tied together, here's the problem that we're trying to solve, and here's how we solved that problem. So you've built a system that turns the lights on and off and turns the air conditioners on and off. But I didn't see a connection between between what you did and the problem that your customer or your advisor or somebody said, I need something that does this, it does X, Y, and Z. Did I miss that, or did you actually skip those steps? Or maybe you described the wrong problem when you started describing the solution. Maybe that wasn't really the problem that you had. So tell me, did I just miss it, or did you have the wrong problem for
No, I think it's a little bit of both. You didn't miss it. So if Alex could go back to slide 4, really, slide 4, 5, and 6. We do talk about it, but it just had to do with the fact, like because we don't really have that much of a time to really establish much of the problem. So that's probably our own shortcoming, really. So we did try to gloss over, but the main issue really is that in the USA, about 40% of all energy consumption is with heat HVAC systems, and are about 30% of all the energy produced is through coal, right, and other dirty sources, which then leads to more greenhouse gas emissions. So it's more of a broad effect problem if we can really look back, right? So we're really tracing back a lot here. So essentially, it is the issue of climate change, accelerated by the emission of greenhouse gases like CO2 and methane. And what we're trying to do here.
Allow me to interrupt for a time. Sorry. But I heard you start, some of your team members say, we wanted it to do this, we wanted it to do that, we did this. Was there, is that because you saved more greenhouse gases if you made it battery powered or if you made it portable? If reducing energy consumption was the problem you're trying to solve, that obligates you as the team now to show how every decision you made was making that problem better. I think that wasn't really, it sounds like that wasn't really the problem you were trying to solve. The problem you were trying to solve was turn the lights off, make the air conditioner easier to control. And you're assuming that that's going to have the outcome. So you missed a step in the middle, and it would have, the presentation would have worked better if you had told us the real problem you were trying to solve and showed how your project turned the lights on and off when you were told they were supposed to go on and off, or things like that. So it's a broad, and it may be a little obscure problem. But when you start out talking about energy consumption and then you jump to a project that turns lights on and off, we've missed a step, and you lose the audience when you do that. You got to bring us along one step at a time.
Right. Yeah, I think that definitely was glossed over, for sure. Now that you say it, now it makes more sense.
And furthermore, then you obligate yourself when you get to the end is that that's the problem you're solved. You've got to test your project to show that it meets that requirement, that it does it does solve the problem you were talking about. So if you tested something else, that means that wasn't really the problem you were trying to solve.
Okay. Yeah, I think we just went over with the assumption that, if you can't turn off lights much more efficiently, then it was like save more energy, but didn't really. And I think some of our previous presentations for the class itself probably had more information there, but we didn't migrate that here. So
understand. Okay, thank you.
Maybe in the interest of time, I'll just make a brief comment. I'll say, I think everybody on this team seemed to know the project very well. I think it sounded like everybody was pretty well involved in the technical portions of the project. I agree with Alan. I think we kind of jumped from there's a climate change problem to this is the automated smart building solution that we're working on. So I'll leave it there. That's not really a question, more of a comment. And Tommy, I'll let you jump in if you have any specific questions.
Nothing specific, I will tell you. So the building I'm in, they put in new lights, LED lights, and they do turn off if there's no motion nearby. It saved the owner a lot of money for one thing, but think about the amount of energy it saved. More efficient lighting, turns off when there's not activity in the area. So those are the kinds of things that you could use to kind of make the point that everybody's been kind of asking you about. We got a good feel for it. I could design the system and everybody understood it. Those are all the good things, and it's just to that same point. So that's all.
Yep. Thank you.
Thank you, everybody. So you may share your slides, and the next team is team 4. Okay, and all members turn on your camera.
Good evening.
It's all yours. Go.
Hello, everyone. This is team. Oh, are you? Okay. Hello, everyone. This is team. What's going on?
We can hear you. You're good to go.
Okay. Hello, everyone. This is team 4 working on the OMRON rotor, the OMRON PLC rotor machine. Our team leader is Parsa. My name is Hussein. We also have Jesus and Eric in our group as well. Our project manager is Dr. Pei. Our faculty sponsor is Dr. Chambetta, and our sponsor is OMRON. So to begin, many prospective students begin their college visits undecided and unsure of what they want to study throughout their college careers. And the world is always in need of engineers. So engineers accelerate human innovations and further the development of new technologies, which can address many of the problems in today's society. It is important to find a way to capture and motivate these prospective students to the engineering program. As you can see here on the graph to the right, according to educationdata.org, out of 2.038 million bachelor degrees earned in 2020, only 5.91% of them were engineering. This leads me to the problem that this project is looking to solve, which is the recruitment issue that the ECE department has here at the University of Houston. With the OMRON equipment given in the ECE lab, we were challenged by our faculty sponsor to present a wow factor to visiting students. Currently, there is nothing presentable or interactive during the university tour that will leave students more interested and eager to find out what the engineering students do here at the university. As of the fall 2021 semester, as you can see here on the right, the University of Houston is ranked behind its Texas competitors when it comes to the number of electrical engineering students, where the University of Houston has about 507 undergraduate and graduate students. Texas A&M University has about 1,500 undergraduate alone. So our solution is to use this project as a recruitment strategy to bring more prospective students into the ECE department here at the University of Houston. We will be doing that by having the OMRON PLC engrave the students' names on a piece of tablet. The students will be able to keep this tablet as a souvenir, and the hope is that it encourages them to learn more about our engineering department. This project showcases the skills learned here, as there will be a current engineering student walking throughout the engraving process with the visiting students. That way, like, students understand the engineering behind the souvenir rather than just taking the souvenir home with no context. So here's the solution diagram. So to start off, there's a GUI on a computer in the lab that has an admin tab and a user tab, where the admin tab authenticates the user to be able to access the configuration window, and the user tab where the student inserts their name to engrave. So the GUI communicates with the PLC through Ethernet IP communications, and the PLC communicates with the gantry arm with I/O communications through motor drivers. And then the gantry arm then proceeds to engrave.
Our project has two main deliverables, which have their own features listed as well. The first one is the user-friendly graphical user interface, or the GUI. Three features of the GUI are to have reliable communication with PLC, to have access to configurable engraving parameters, and to initiate engraving and receive progress and or error data. The second deliverable is the automated engraving system. Two features of the automated engraving system are to automatically execute corresponding motions for each selected letter, and to control the engraving tool by adjusting its speed or enabling or disabling it. Here we see the flowchart of tasks, and as you see, they are in 4 categories that are color-coded. First, we had to learn about ladder logic and Sysmax Studio, which are the language and the development environment of the OMRON PLC, respectively. Second, we implemented a reliable middleware to establish communication between the PC and the PLC. However, this task has faced some setbacks and is incomplete. Third, we developed the GUI and all other necessary algorithms to properly engrave each letter. Lastly, we installed the router and developed the ladder logic code to automate the execution of motion instructions for each letter.
So just to make very clear what the issue for our current product is, this is our intended pipeline. We want to have the GUI, PLC, and gantry communicating with one another directly in order to automate the engraving process. However, OMRON has furnished us with an incomplete version of what's called CX Composite, which is OMRON's proprietary tool for communicating between their PLCs and external computers. This being the case, it isn't possible with the current tools available to us to establish communication between the GUI and the PLC. In total, we've been waiting for 10 weeks for OMRON to get back to us with a working version of their tool, 6 weeks for the incomplete version, which we now have, and we've been waiting additional 4 for the DLL that we're currently missing. Until they get back to us with the missing part, our workaround has been to monitor the values which are set by the GUI and PLC and then manually update fields on the other side correspondingly. This emulation of OMRON's communication protocol has been sufficient for us to be able to test most of our engineering specs. And once OMRON gets back to us with the missing component, it should just be plug and play because we've already written the software we need to handle the communication using CX Composite. So with that out of the way, we're going to jump into our specifications. We'll break these down on future slides, but the key thing to note here is the colors. Green specs are fully complete, yellow are partially complete, red are incomplete. And we'll justify the state of each of those specs one at a time. So our first specification concerns the legibility of engraved text. The main factors which will impact the legibility of our engraving are the consistencies of the depth and width of the engraving. In testing, we found that the widths of the engraved characters fell within 15% of the target at all measured points along tested characters, disregarding the stray wood shavings you can see in the picture. This is slightly outside of our target range of 10%, but a lot of that is attributable to the narrow bit we're currently engraving with, as you see on the right. In terms of engraving depth consistency, we didn't hit our original target. We discovered that the lab's gantry engraving surface is slightly warped to the tune of about 1/12 of an inch at various points along the surface. And while that's not a lot, the wood we're engraving is only 1/4 of an inch thick. And so this minor warping results in around a 30% deviation in engraving depth. Despite this, when we engraved at a normal depth, we found that this deviation wasn't visible and the text is still very legible. So consequently, while we didn't strictly satisfy our original legibility criteria, it's our current belief that our original targets were unduly stringent. And so that's why we've given ourselves a partial rating on this specification. Our second spec is text scaling. In order to fit larger names on a smaller piece of wood, we want to compress long text horizontally. Our target is for names to occupy up to 80% of the maximum width of the board, with the rest being left as a bezel. To accomplish this, we wrote an algorithm which the GUI runs to estimate the width of an entered string. When the GUI sends the string to the PLC for engraving, it also sends a compression factor, which the PLC uses to scale the motion of its motors. In testing, we found that the algorithm compressed text accurately, and we were able to regulate text width with floating point precision, which is sufficient for our spec. The third spec is engraving time. We anticipate that touring students will visit a lab in sizable groups. We don't want to keep them all waiting in a long line to get their names engraved. In order to keep the wait times manageable, we set a target engraving time of 5 seconds per character. We found that while some characters take longer than others, printing various strings took an average around 4.5 seconds per character, which satisfies our spec barely.
Our fourth spec concerns the accuracy with which the data entered by the user ends up being represented correctly on the final engraved product. We basically want to confirm that the content received on the PLC registers matches with what was input to the GUI. For this, we wanted to implement the most reliable middleware. Based on our research, the CX Composite middleware is the best choice since it is compatible with both the GUI software and the OMRON PLC. As of now, however, there is an issue with the software where it is missing a DLL file, and therefore we have marked this spec as partially complete because of the missing bridge between the GUI and the PLC. Our fifth spec is engraving precision, which is essentially how accurately our instructions to the PLC get put into practice on the target board. For example, if we command the gantry to engrave a 1-inch line, the maximum deviation error on the inch it draws is the question we're trying to address here. What you see in the image here is one of our early engraving attempts. We tried to write the same thing twice in a row in the same place, and you can see the accuracy is not great. The E and A are in different places. The B is way off, and so we had an issue here meeting our target of 0.2 inches maximum deviation. We realized that the target board was being moved during the engraving, and therefore we had to secure it better. With some tuning and better clamping of the board in place, which you can see circled here, we eventually got to a point where the results are pretty much perfectly accurate. We printed a ruler on the gantry and compared it with an actual ruler, and each tick of the ruler matched up with the engraving within 0.2 inches. The second to last spec for our project concerns what happens when the gantry motors try to travel in a direction which is outside the bounds of the gantry. The gantry comes with switches which can detect border proximity, as shown in the picture. And so our last spec was to capture the toggling of these switches and execute an interrupt to terminate our program's execution when these switches are triggered. The interrupt works, and we have successfully prevented damage to the gantry as a result, which remain operational. The final spec is the only one we haven't even properly attempted. We wanted to quantify the ease of use of our product for touring students by having non-engineering students test our product and rate its ease of use on a scale of 1 to 5. Unfortunately, since we are still missing that OMRON software component, we have to do some of the work manually to get things working. And so this survey isn't really feasible for us to implement at this time. So to summarize, out of our 7 engineering specs, we have fulfilled 4 of them completely, partially completed 2 others, and not attempted 1. All of our unsatisfied specs ultimately boil down to lacking a critical software component from OMRON, which we are still in the process of acquiring.
Our accomplishments include an easy-to-use GUI where the user can enter their name and the admin can adjust the gantry speed, the size and engraving medium, the engraving depth, and as well as the font size and engraving. We also fully programmed the ladder logic and structured text needed to move the gantry arm in the motion to write out 26 letters of the English alphabet.
So now we're going to show a demo of the main components of our project. Here we have the PLC engraving the names of the team members sequentially on a sample board. And after this, we'll show off the user interface as well. So just to note, what you're seeing here, this motor is currently running off of a 24-volt digital port, but actually the motor is rated at 48 volts. So we believe we could engrave faster and to a higher quality if we got the motor running at full speed. So even given what you're seeing here, we see that there's room for improvement.
And here is the video demo for the GUI. What you see is the fully developed GUI. As seen, we have a user tab where we can input the name and receive engraving progress or errors. We also have an admin tab where after authentication, we can access the configuration settings window to update the engraving parameters as needed. As an example here, I input my name and click submit, after which I receive the engraving status.
So a major setback with the project was the use of circular motion with the PLC. We originally intended to make the program letters look more curved. So our solution to the setback was to program the motion to disregard circular designs and mock the circular motion by using completely linear and slanted lines to give the appearance of the curves. And by far, our biggest setback was receiving the software we needed to connect the software and hardware parts of the project. So it took us about 6 weeks to receive the software, and when we did receive it, there was a DLL file missing, and without the file, we were unable to get communication established between the PC and the PLC, and we still have not heard back from OMRON after inquiring about the file. So some lessons learned. Throughout the time we have worked on this project, we have learned a variety of skills, technical and non-technical. A valuable skill that we can take with us is team communication and scheduling. We needed to make a schedule to meet and work on these presentations and report, and also work on the project itself. So we sought that communication with management. We also sought that communication with management or the consumer is essential to tracking the status of the project to make sure deadlines are met, update them on risk assessment, and tasks are understood by both parties. We'll need to communicate with our supervisors to talk about the risk so we can offload some of the risk off of the engineers and enable the engineers to take risks to advance the project. Another important skill we developed that can be applied to our future is alternative methods to do some tasks we needed to do. So like our circular motion, we had to change the way we designed our letters. So now some advice for the next team. Some technical advice for the next team would be to try and see if OMRON has responded to get that missing DLL file to establish the PC to PLC communication. We also think that the next team should optimize the gantry to be faster by researching possible methods to power the drill. And for some general advice, we think that they should reach out for technical support from OMRON early on because of response times from them. And they should also ensure that the entire team communicates throughout the semester, not just before something is due. And also when taking on a project without knowing about the subject, ensure that there are resources out there to learn from due to having trouble getting technical support from OMRON.
Perfect. Now we're open for Q&A.
Timing is perfect. Okay. Tommy, do you want to go first?
Sure. I don't have a lot. I did notice that from our viewpoint, on my end, there's a usability that you had trouble achieving that part of it where you had that GUI, I believe. Go back to that slide if you would, where you show your goals. There we go. That user interface. So there
Is it this one? Or?
There was the one with yeah, that one.
This one?
Nope. The one with the red line across the bottom. You've got all your there we go.
Yes,
User
specification.
interface, ease of use. Now, basically, you were trying to do a survey. I will tell you there are there's actually usability standards and how you actually do that evaluation. But why? Explain to me why you had this failure again with the usability.
I can cover that if you guys want.
Go ahead.
So if we can go back to slide, I think 10. That one. So the fundamental issue is that because we can't automate the connection between the GUI and the PLC without this software component from OMRON, if we were to bring in a non-engineering student to use our device in order to evaluate its ease of use, they would enter something into the GUI. We would read out what that GUI prints and take that string, manually enter it into the PLC, and then it would engrave from there, which isn't really, I mean, the ideal is you have it all automated. And that's the component we need from OMRON, is just this communication here. With things that being the way they are, it wouldn't be an accurate representation of how easy it is to use when we have to go in manually and drag information from the GUI to the PLC and back. It's a limitation of our.
To add on what Eric is saying is basically part of our deliverable was to have a user-friendly user interface so that the students can come in and interact with that and put in their name, click submit, and that name goes through the PLC rather than trying to input that information themselves to the PLC. And in order to establish that communication between these two, you need to have that middleware, but also that's not the only sole purpose of that middleware, because that middleware is much more powerful. It is compatible with C# libraries. So you can, it's not just about transferring a string of data from the PC to the PLC. You can transfer all other sorts of information. And it just makes your job a lot easier in terms of interacting with the PLC because you can do it on your personal computer. It's a very powerful piece of software. And we did receive it late. And even when we received it, it was still missing a DLL file because we tried to run it with our own program. And when we ran it, it was giving an error which indicated a DLL file is missing.
Yeah. So the one thing you stated early was that you were trying to maybe create something that would make engineering look more attractive to other students as they were going through their tours of U of H. Did you try to do any measurement of how effective that was?
So the measurement would have been along with the survey we wanted to make, but we never got to that point because we wanted to see, first of all, how easy our piece of system is for the students to use, but also to see, but also to have a engineering student, a current senior design engineering student, to walk them through throughout the process. So when they get there and they're interacting with the software, with the GUI, another engineering student would be explaining to them that like what you're inputting right now is being translated to the PLC in this way, and this is how the motors in X, Y, Z axis are being synchronized to do these desired motions. So that was the goal, but we just we never reached that point.
Well, I got you. I was just curious if you had anything in that. That's all for me.
Alan, I appreciate your time.
Alan, I think Carrie left already, so it's yours.
Oh, great. So you guys get the prize for showing your tests against your engineering specifications. So that there's in real life here that when you're making something, it's got to do whatever the requirements are when you came in, and then you got to implement something and then test it to see if it does. And if it doesn't, you, just like you guys did, you changed it because it didn't meet your specification. So that was, you guys did that better than any of the teams here tonight. So you get that prize. I thought of the same question that Tommy had about the wow factor. It sounds to me like the wow factor, you mentioned that as a problem that you were trying to solve, but I suspect, well, tell me, did you decide that in order to meet that wow factor, you would go engrave their name? Or did somebody tell you, we want this engraver to grave somebody's name because we think that, so that now becomes somebody giving you a requirement to engrave their name rather than to come up with something that has a wow factor? Which one?
So what happened was at the beginning of the semester, Dr. Trombetta, faculty sponsor, approached us and asked us to come up with a wow factor using the equipment that's already available in the lab, specifically the PLC, because what we're doing here is already done with CNC machines, even probably way better. But the challenge was to use PLC to show the power of PLC and its applications, but also the challenge was we were restricted to only using the PLC, and also he wanted us to specifically engrave something. And but he was not sure what exactly that would be. It would be a shape, it would be like somebody take a picture and then translate that information to engrave, which is way more complicated. Like we were already struggling with just like getting these letters, proper motion and synchronizing motors. So we were kind of limited with the equipment we were given, and also initially Dr. Trombetta wanted us to specifically do engraving. So that's not something that we came up with.
So it sounds like engraving the person's name was a negotiated requirement, which happens in real life. You get with your customer and I want something like this, and you say, well, I can do this, but I can't do that, or that one will cost you an extra year and another $1 million. So yeah, so you negotiate the requirements. Now, it appeared to me that the engraving was it was not really high quality engraving. The vertical, well, you had trouble repeating. You had very excellent specs on what makes a good engraver, or at least you had specs. But these are not really precise letters that this thing makes, and so the amount of wow factor you have here, when the next team figures out what they want to, how to make it better, that's going to be one of the things that they could look at. And how do we have an output that has more wow to it, or how do you enhance that wow? But you guys did a great job of showing. Here was the requirement that we negotiated with our customer, Dr. Trombetta, and here's what we did to test it and make changes when we didn't hit it.
Yeah, for sure.
Well, I'm sure you're going to say the same thing I would, Parsa, which is the precision did improve a lot by improving the clamping that we were using. So you can see these holes even on this slide in the bottom left image, the holes in the top left and bottom right of that image. We actually basically sort of screw the board onto the gantry, and in that way we've dramatically improved the precision. The other thing I'd say on that is that I think if we were to increase the motor speed without necessarily increasing the rate of the engraver, like in terms of like inches per second, we could get a higher number of revolutions, and that would iron out some of the rough edges on like within a single line. So we do believe that there's room for improvement. We've done a fair bit to come from. If we go back a couple slides.
To improve the quality of the engraving or the result.
So this one was very early, and this was before we had the clamping that we currently do. We've improved this a lot, but there is definitely still room to improve. I think we would all agree on that.
Yeah, for sure, because this is also something we just started. So using the PLC and the gantry arm, other teams are using for different purposes as well, but specifically doing engraving and this type of project, it was the first. So we are the first team that worked on this. We have basically figured out how to do like all the motions that you see. Like as we mentioned, we struggled figuring out the circular motion as well. That's another factor that affects how our litters are looking. Because we couldn't figure out how to do circular motion. It was kind of hard to synchronize motors. There are function blocks built in PLC, but we just could never figure it out, and we couldn't get support from OMRON regarding that. So we came up with our own solution, which is to use these incremental linear motion to print different letters. We came a long way in terms of figuring out how to use the ladder logic to control the motors. But if for future teams, if they figure out how to fix that DLL problem with the software, there would be room to do even more complicated tasks like scanning pictures, uploading that, trying to figure out the motion on that. And like what Eric said, if you increase the speed of the motor and some more fine tuning, you can definitely improve the quality, and you can do more complex tasks. But yeah,
it's very easy to send data to the PLC once we have the CX component working. It's a completely trivial, so we can send any kind of information and engrave that. So yeah, like you said, it could be pictures. You know, you take a picture with a camera, it gets scanned, and then that gets into the PLC and that gets engraved. I mean, that would take some engineering, but that's definitely something that's within the realm of possibility, and that would be much more of a wow factor than what the implementation that we have right now.
Yeah, and to add more to that wow factor, I mean, this is showing all 4 names on one piece of board. I think if we just did that to show that we're able to print different names, but we are able to just print one on a little piece of tablet. And I think that would look much better and wow students much more if it's like in a better looking piece of wood than this one, and and just one name on there. And that small boundaries, it would look much better, I believe.
Yeah, using solid wood might engrave better than particle board too. So, but it will cost a lot more.
Yes.
All kinds of experiments.
We can make the board smaller. Well, but I can see you guys are really enjoying the project, so that's wonderful. That's a very important part of the project here. I would like to thank all the presenters. I think that the wonderful work you have done. I enjoyed the semester working with all of you. Any of the Alan and Tommy, do you have some last word to say to the whole class? Last advice?
I will say that you kind of have faced some of the problems that are out there from when you're dealing with projects, and that's learning how to learn. Basically, that's what you've been taught in school, is how to learn, and then you just had to kind of dig in and apply those skills that you've been waiting so long to see if they're going to do you something. So this was, I think, you applied them well and moved something forward, and now you feel a little more confidence in yourself, and that's part of moving forward and taking on more responsibility and more complex things. This is how you do it. So the things you did were right in that problem solving kind of element that project engineers do all the time. You many times get faced with things that you don't have a lot of background in, and that's when you have to go learn about them and then come up with solutions. So yeah, good luck. I mean, good job.
Alan?
Appreciate it.
Yeah.
Thank you.
Yeah, I would second that. It's the real world, the stuff you learned in school are just the tools in your toolbox, and of course, it's not a course in how do I think, how do I solve a problem. When the problems have variables you could never predict. So hopefully these projects, we've been talking to the faculty for years about how to organize it, specifications and tests that show you meet the specification, and communication, oral and written communication, and so the courses you see it is refinement that I've seen going on in the courses for over 10 years and maybe 20 years at U of H. So this is really good. Learning how to use the tools that you get out of the textbooks to go solve real problems and then figure out what to do if it doesn't work. So yeah, all of the teams showed they ran across things that didn't work the way they thought it would when they started, and they had to adapt and go figure out what to do next. So that's great. That's showing that you're getting ready for customers and bosses telling you things, and you got to go figure out how to do it, even if it may not work right the first time.
And it may not make sense at all.
Even if bosses don't make sense a lot of times. Yeah.
Well, I hope that you got a little bit taste of the real world, but still we are far away from that. So hopefully we make a small step toward that direction. Thank you, everybody. And thank you, all IAB members, Alan and Tommy. Good night.
Thank you. Thank you for your time. I appreciate it.
Okay. Good night,
Stephen,
everyone. Yeah.
Stephen, are we supposed to email these rubrics to you?
Yes, that would be great.
Okay, we will do that.
Maybe email to your team leader and CC me. Either way.
I have a team leader.
I don't know. I'm not sure about the IAB structure there.
I don't know. I sent it to you and Desiree.
That would be fine. I'll take care of it. Thank you very much. Really appreciate your time.
Thank you.
Thank you. Thank you.
Thank you.
Bye-bye.
Bye.
That's it.